All right. So on Tuesday, we finished off and we said, okay, well, if we have some desired margin of error, okay, and some confidence level that we want to have in our report, right? So before we even collect any data, right, we're gonna have some idea of what margin of error we're comfortable reporting at and what confidence level we would ideally be reporting at. And from there, we can calculate what sample size we would need. Okay? So then we went through and we reorganized the formula to solve for n. And then this is where we kind of got to. Okay. So what I'm going to do is I'm going to steal this copy and bring it into today's notes. So continuing from last day. Oh, that looks weird. Why isn't this on a line? There, that's better. Okay, so we solve for n, right? Where m is the margin of error, right? Z star comes from the confidence level that we want, right? And then p hat, q hat, right? And then so where I rushed through and I said, okay, well, if we have a previous sample proportion, right? So from a sample the year before or something like that, then we can use that as our p hat, okay? If we don't, remember, we haven't collected a sample yet, so we're not going to have a current sample proportion. So if we don't, then we're going to use 0.5 instead, okay? Which gives us the most conservative estimate of n, which really just means it maximizes the value of n that we could possibly need, okay? So because we have two options for p hat, we usually just denote them in formulas. We use p star instead, right? Just so there's no confusion. Although I guess adding notation can be confusing. Okay, but here I'm going to say, I guess I should clarify that this here is from last day. Whee! So then since there are two options for p hat, we usually denote it by p star instead, just a placeholder. We usually denote it by p star. Yeah. Where p star is going to be p hat if we have a previous sample proportion from a previous sample. And a lot of kind of data analysis firms will have previous samples, right? And so the reason we would use that is because 0.5 and 0.5 maximizes our n, right? But collecting a large sample is expensive, right? So if we don't have to do that, if we have an idea of what the sample proportion is, then we can use that instead, or p star is 0.5. If no previous sample exists, or in our case, if no information about a previous sample was given. One thing about N, right? N is a sample size, right? And so we're basically saying, okay, how many people do I need to survey? Of course, we're gonna likely end up with a fraction, right? So some decimal answer here. But the thing with N is that we always have to round up, right? I can't sample 0.1 of a person, right? And so we always round up, even if rounding rules say that we should round down. And the reason for that is because we did this calculation trying to achieve this margin of error. A smaller margin of error is good, right? But a larger one than we wanted initially is bad, right? And we could play around with the numbers, but what I'm saying is if you decrease your sample size, so if you lower it, then your M is going to increase just slightly, and that's bad, right? So in that case, that's why we always round up. Okay. So here, remember, oops, N is the sample size. Which must be a whole number. Which must be a whole number. Okay. And we always round up. And we always round up. Okay. So just as an example, right, if you find that N is 110.04, even if it's something super small like that, right, we would need 111 in order to satisfy the criteria that we set out. Okay. We would need N 111. Yeah. So that's really important. Okay. How about we do an example? And I picked them out already from the textbook, of course. Not of course, sometimes I have my own up my sleeve that I prefer. So it is referring to a previous exercise, but we have everything that we need in this blurb, so that's fine. So we're looking at the results of a poll evaluating support for a generic national health plan in the US in 2019, which reported that 55% of independents are supportive, so in support of this national health plan. If we wanted to estimate this number to within 1% with 90% confidence, what would be an appropriate sample size? And so that's what tells me, okay, I need to solve for N, right? So that's good. And the sneaky part here is we are given a margin of error, but it doesn't say we need this margin of error to be 1%, right? But when it says to within 1%, this means that M is 0.01, remembering that we're talking in terms of proportions, right? So 1% is 0.01. Yeah. So really what this means is if we wanted to estimate this, and maybe I should use a different color, wanted to estimate this number to within 1%, really what this is saying is that we want p hat plus minus 0.01. And we're also told that we want it at a 90% confidence level, which means that we need to find Z star for a 90% confidence level. You can use the tables if you want. Back in my day, we had to memorize them. Just the core ones. 90, 95, 98, that kind of thing. Okay, so 90 has a Z star of 1.45. So here, this tells me that Z star is 1.645. So we also have a sample proportion from 2019, right? So that would be a previous sample proportion of 0.55. So in this case, move it over here, we have a previous p hat of 0.55. So, all right. So we've been given a lot of information in the question, of course, right? So it's our job to kind of pull it apart and make sure that we've checked all our boxes here. And if we try to calculate our sample size, right, a nice way to do that is to write out our formula and then just make sure that I have all the information that I need. So I'm going to need to solve for n, which is Z star over M squared times P star Q star. Now, I want you to be used to this because this is how I have it on the formula sheet that's attached to your assignment, as well as the quiz, or that you will have on the quiz, right? So just be comfortable with that. But there are two options for P star. In our case, right, P star, we will use the previous P hat equal to 0.55 as our P star. As soon as we have something, we're going to use that instead, right? Save ourselves a little bit of money in terms of how many people we want to sample. I have Z star, I have M, I have P star, therefore I have Q star. So we're ready. Here we go. So I have 1.645 divided by 0.01 squared times 0.55 times 0.45. Often I skip writing the 1 minus. Sometimes I do it. Unpredictable. So my n then is going to be, and I have it here, 6,697.411875, right? But also remembering that we need to round up. So my final sample size must be 6,698. Make a note here, right? Can't sample 0.4119 of a person. So we need to round up. So then, going back to this question here, right? If we wanted to estimate this number, so the sample or the population proportion rather, to within 1% with 90% confidence, we would need a sample size of 6,698 people in our survey or in our poll. Yeah. Just to illustrate the difference between the conservative estimate and using the previous sample, of course, 0.55 and 0.5, there's not a huge difference, right? But if I use 0.5, I know I'm going to get a larger sample size, but how much larger? Okay, so what if What if we didn't have a previous p hat? Then we're going to use p star equal to 0.5. So I used to work for a market research firm, and I think once you've done a few of these calculations, you'll see that they're not bad, right? They're pretty easy calculations to do. But when I worked at this market research firm, of course, they do a lot of polls, they do a lot of surveys, right? Need to calculate the sample size, and we do exactly this. But some people had these like wheels where you adjusted different portions of the wheel to say what your margin of error is going to be, what confidence level, and then it gave you the sample size. So then when I showed them the calculation, their minds were blown. They should have probably seen it at some point, but who knows? We forget, don't we? All right, so if we do this with just 0.5 instead of 0.55, how does it change? Everything else stays the same, 1.645 over 0.01 squared, and then 0.5 times 0.5. I get 6,765.0625, still rounding up, 6,766. Okay, not a huge difference, right? 6,766 is more than 6,698. So if I don't need to have this many, right, that's great. But if we wanted to be super, super, super safe, then you could go for this value, right? But depending on what's given in the question, then you're expected to know, okay, if I have a previous one, a previous sample proportion, I'm going to use that. If I don't, I use 0.5. All right. So that wraps up 6.1, one sample proportion, right? It's also what we focused on in chapter 5. So that's going to be a big player. We had to develop all these concepts, right? And I agree, we haven't done a ton of examples or anything. I know that. Okay? That's where the assignments are going to have to come in for you to practice. Are you guys ready for your second type of question? Oh my gosh, you've been waiting so long. Finally, another type to keep track of. Can't wait. What if we don't just have one sample proportion? What if I have two sample proportions? I want to compare these sample proportions, right? For example, here, right? Some proportion of independents and some proportion of, I don't know, Democrats, let's say, would be in favor of the National Health Plan. What if I wanted to compare those two groups, right? The proportions from those two groups. Well, look no further than 6.2, the difference of two proportions. I usually call this question type 2 sample proportions, just to kind of nudge you in the direction of that you have two samples and a proportion from each of them and you want to compare them. Two sample proportions. Just kind of on the fly, right? If I asked you to compare 0.5 with 0.4, where would you start? You'd probably say, well, 0.5 is 0.1 more than 0.4, right? You would take the difference, right? And so in order to compare two groups, we consider the difference. So to compare two sample proportions. Bless you. We consider the difference in the proportions, right? Seems like a logical thing to do, right? It's where our heads went, hopefully. I don't know what else you would do. If you wanted to compare two numbers, all you really can do is look at the difference. So to compare two sample proportions, we consider the difference in proportions. Now, because I have two samples, sample one, sample two, population one, population two, then of course I'm gonna need to denote that some way, and I do that using subscripts, right? And so really what we're gonna look at is P1 minus P2. Okay. Population proportion of population one, population proportion of population two. Okay. This is what we're going to build confidence intervals to try to capture. This is what we're going to hypothesize about, right? And so this is now the thing that we're doing inference about. Okay, so this is what we do inference about in a two sample proportion question. Huh? So just like before, right, in the one sample proportion case, I need a point estimate for this thing, right? So now it looks a little bit beefier, right? It's not just P, now it's P1 minus P2, but we do the same thing, right? My point estimate, my best guess is going to be P1 hat minus P2 hat. Okay. Notice that 1, 2 are generic, right? As long as you're consistent in which group is group 1 and which group is group 2, the order does not matter. Okay. And as you have more practice, you're going to be, I, for example, don't like negatives. I prefer to work with positive numbers. So usually I do the subtraction that gives me positive numbers. Okay. That's a little sneaky, right? But that's just because that's what I prefer. But for now, let's just kind of keep it simple. But you can get jiggy with it as long as you're consistent. Okay. So let's just write a little note here. As long as you are consistent with your group assignments, right, then the order doesn't matter. With the group assignments, order does not matter. All right. So like I said, the point estimate is going to be P1 hat minus P2 hat, just generically. The point estimate for P1 minus P2, wait, that doesn't look like a 2. Will be P1 hat minus P2 hat. Okay. So that means that we're going to need the standard error of this point estimate. All right. So that's the next thing that we need. But in order to get that, we need to check our conditions. Okay. So the next thing we need is the standard error of the point estimate. Which leads me to the conditions, which I am going to steal from the textbook. Okay. Just like before, right? These conditions are the same, except now I have two samples. And so I need to do everything for both samples, right? And so, and our goal again is to be able to use the normal distribution. And if these, so when these conditions are satisfied, then we'll know the standard error is this, right? So let's talk about the conditions and just kind of reassure ourselves that the conditions have not changed. We just need to apply the conditions to both samples now. Okay. So the independence condition, okay. Remember before we had to have a randomly selected sample and that let us assume independence. Okay. But now we have to extend it a little bit and say that the data are independent within and between the groups, right? So one way to do that is just to randomly sample both groups, and then we're able to assume that both within the groups and between the groups is going to be independent. Okay. So it's still the same way to get there, right? It's just that we have to check between and within the groups. Okay. So generally, this is satisfied if the data come from two independent random samples, or if the data come from a randomized experiment. Okay. What we're going to find is a lot of our examples come from health data, right? So kind of research studies. What happens if you have a pacemaker? I think the example I pulled is about fish oil. Right? Does it reduce the amount of heart attacks in patients? That kind of thing. Okay. So the independence condition is the same. We just need to check it for both groups. Okay. The success failure condition has to hold for both groups, right? So that means I need to have at least 10 successes and at least 10 failures in each of the groups or in both groups. Okay. And so those success failures for the confidence interval, those are the observed ones. For the hypothesis testing, it changes just slightly, but we're not there yet. We're going to start with confidence interval. Okay. Nice and slow. Okay. So everything stays the same. We just do it twice, essentially. Okay. Once for each sample. So then the standard error is going to be the square root of P1 Q1 over N1 plus P2 Q2 over N2. Okay. Or if you prefer to write it 1 minus P, 1 minus P2, or 1 minus P1, 1 minus P2, that's fine. I think it looks a little bit less daunting if I use the Q's. And so I'm going to rewrite this as the standard error of P1 hat minus P2 hat is going to be the square root of P1 Q1 over N1 plus P2 Q2 over N2. Looks similar, right? If you just focus on one group, it looks similar to just the one sample proportion, but now we have two. Okay. And we can't subtract the standard errors because we have more spread if we're considering two. That's how I think about it. Okay. We run into the same problem that we had before, right? I don't have the population proportion for group one. I don't have the population proportion for group 2. So we need to find some better way to estimate these things. For a confidence interval, we're just going to use P1 hat and P2 hat, okay, which is exactly what we did in the one sample case. All right. So here, if we recall the general formula for a confidence interval, the general formula for a confidence interval, it was what? It was the point estimate, right? In general, it's going to be a point estimate plus minus. I'm still going to use Z star, but eventually I'm just going to swap this out for a generic critical value. Hard to say. Critical value. It won't always be Z star, but for now it is. And then times the standard error of the point estimate. So now, for the difference in two proportions, the point estimate we said was P1 hat minus P2 hat. I'm going to put it in brackets just to emphasize that it's one value, right? So that you don't do something weird with the plus minus. Because then we do plus minus Z star times the standard error of the point estimate is going to be P1 Q1 over N1 plus P2 Q2 over N2. And for the confidence interval, we're just going to estimate those with the P hats. In confidence intervals or CIs, we use P1 hat to estimate P1 and P2 hat to estimate P2. Just be aware, just like in the one sample case, the standard error changes slightly when we move to a hypothesis test, because then I have some null hypothesized difference of proportions, right? And so then I would use that instead. But we're not there yet. Okay. Here's the formula that we're going to use. I think we're ready for an example where we apply this. I chose this question because it has a lot more information than we need to have, right? We're going to use it in our favor, but sometimes when we're first learning to read these questions, right, having this amount of information is a little bit daunting, right? Because what am I supposed to be using here? Okay, so I'm going to kind of walk you through it. All right. So a 5-year experiment was conducted to evaluate the effectiveness of fish oils on reducing cardiovascular events, where each subject was randomized into one of 2 treatment groups. Okay, randomized, that's good. We'll consider heart attack outcomes in these patients. Okay, so they were randomly assigned to, okay, you're going to take a fish oil, you're going to take a placebo. You don't say that, obviously. Here you go, here you go, here you go. Right, and then over a 5-year term, you just sit back, relax, and see if anyone has a heart attack, right? People do have heart attacks, right? But a lot of people didn't, obviously. And so, and then we've got the total here. Okay, we're going to be more interested in the proportion of people who had heart attacks, right? That's what we're concerned about. Okay. Create a 95% confidence interval for the effect of fish oils on heart attacks for patients who are well represented by those in the study. If you think about a study, right, especially one that's talking about heart attacks, you're not going to mix, 20-year-olds with 70-year-olds, right? You're going to have a very set number of demographics that you're going to reach in your study, right? So then this study would only extend to that demographic. Okay, so that's important, but that's all they're saying here, who are well represented by those in the study, right? So it doesn't extend to everyone, it extends to that same demographic. We don't know what it is, so it doesn't matter. I think the study itself, there's a link in the textbook if you're interested, but and they would have had to explain it. So we're going to build a confidence interval, but then also interpret the interval in the context of the study. Okay. When we're talking about the difference in proportions, it's a little bit tricky. We still use the same blurb, right, to interpret the confidence interval, but it takes a little bit more effort. Okay. So let's just talk about, so here, either they got the fish oil or placebo. So here are the treatments, I guess plural. And then we either observed a heart attack or we didn't. So those are the outcomes. We're interested in talking about the proportion of patients who had heart attacks in the fish oil category versus the placebo, right? And so for that reason, these are our successes, right? Because I want to talk about the people who had heart attacks. Okay. So what I'm going to do is my sample proportions are going to be these values out of these totals, right? These are successes, these are failures, these are my sample sizes, right? Now, I'm going to let F denote the fish oil group and P denote the placebo, which means I'm going to have a P hat P, which gets kind of weird, but it's the most obvious one. So let F be fish oil and P be the placebo group. That's basically my group 1, group 2. So whenever you can, try to use these question-specific subscripts, right? It'll help you keep track of what values come from where, right? And so if we talk about P hat, and maybe I'll do them side by side here, P hat F, that's the sample proportion of people who have heart attacks in the fish oil group, which is 145 over 12,933. Careful, because they look so similar, but the sample sizes are slightly different. Okay, so just be really careful there. So I get 0.01121162917. I'm going to round that to 4 decimal places, 0.0112. And that's my sample proportion in the fish oil group. How about in the placebo group? We do the same thing. There were 200 who had heart attacks out of 12,938. I'd be really careful. P hat P is going to be 0.01545833977. But I'm going to round to 4 decimal places. 0.0155. I'm going to check the conditions before I go any further. Right. So, the first condition is still independence. The subjects were randomly assigned to a treatment, right? Because it says so here, each subject was randomized into one of two treatment groups, so that's good, right? And because they were randomly assigned to each of the treatment groups, there's no reason to think that there would be dependence between the groups either. Yeah. So subjects were randomly assigned to treatment groups which means I wanted to do a follow-up because we have to touch on the within the groups, but also between the groups. Okay. We can also assume the two groups are independent. Two groups are independent. Success failure is the next condition that we have to check. I need to have at least 10 successes and at least 10 failures in each of the groups, right? And so what we can do is we can just look at these numbers. All right, so I'm going to bring these here. These are the successes and these are the failures. All of these are greater than 10, right? And so it's satisfied. I will show you how to do it with the calculations, even though we don't need them in this case, right? But we see there are at least 10 successes and 10 failures in each group. Right. Or we can check, what would you do if you didn't have this table, right? You would have likely the sample proportions from each group and the sample size. And so then you would have N, and in this case, I guess NF, P F hat, which if you have XF, then that's great, is 145, which is greater than or equal to 10. NF times QF, which is NF minus XF, right? The number of failures, which is 12,788, which is also greater than or equal to 10. This is group 1. We have to do the same thing for group 2. I'm going to do them beside each other here. NP, P hat P, which is XP, which is 200, is greater than or equal to 10. NPQP hat is NP minus XP. And this is where the auto tune would come in handy. 12, 7, 3, 8. Feel like I'm just up here saying gibberish, which would sound good, auto tuned probably, or better. Maybe not good. Group 2, right? So you have to check it for both groups. But notice, right, that saying this, right, we see it and we can back it up with the numbers, right? But this is what we would do if we didn't have just the numbers. Okay. Conditions all check out, they will, right? What does that mean? Therefore, we can use the normal distribution to model the difference in proportions. We can use the normal distribution to model P hat F minus P hat P. That's great. This doesn't look like there. That just means that we can go ahead and use that standard error that we wanted to use, right? And so now we're ready to make our confidence interval, right? So thinking about our confidence interval, right? We've got our point estimate, which we can calculate because we have these proportions, right? So we have everything that we need there. And then we have the critical value that we need, right? Here needs to be for a 95% confidence interval. So we can find that 1.960, but let's just confirm. 95%, 1.960. And we're able to use this as our standard error. So we have everything that we need. So let's hop to plug and check. We want a 95% confidence interval. So Z star is 1.960. I'll start by jotting that down. Just so I'm not scrolling around so much, right? Let's just jot down the information that we have. PF hat was 0.0112, I think. 0.0, and PP hat was, we're going to use 0.0155. We're going to need NF, which was 12,933, and NP, which was 12,938. A little bit sneaky. There. That should be everything that I need. Of course, if you wanted to do all your kind of work up here, you could find your Q's, but I'm gonna get to work here. All right, so our confidence interval looks like this. PF hat minus PP hat. Remembering that that's one value, we want to talk about the difference. Plus minus Z star times the square root of PF hat QF hat over NF plus PP hat QP hat over NP. now we can plug in all our values. So now I have 0.0112 minus 0.0155 plus minus, and just so I'm stacking my plus minus, I'm gonna make a little adjustment there. We said 1.960. And then 0.0112 times 0.9888, right? 1 minus 0.0112 divided by 12,933 plus 0.0155 times 0.9845 divided by 12,938. Slow and steady wins the race here, okay? So you don't want to rush through this. I would recommend simplifying each of these fractions inside, storing those values. Your calculator likely has a store function, right? And so if you want me to check yours out, I can do that, right? But a store function just stores all the decimal places so you don't have to re-enter them. Because even if you re-enter them, some of them are lost, right? Some of them aren't showing. Okay, so you want to keep all your decimal places. Okay. So I would figure out what this fraction is first, store it, figure out what this next fraction is, then add it to that previous value, then take the square root. Don't forget the square root, right? And then multiply by 1.96. Okay. And then I would jot down the margin of error before you lose it all. Okay. So here, keep all decimal places. However you want to do that. All right. So I can figure out what, so that might be a nice way to clean things up. Negative 0.0043 plus minus 1.960. And since I did this morning, I'm just going to jot down, I get 8.56 times 10 to the negative 7. Which means it has 6 zeros in front of it, right? Super, super small. And plus 1.179 times 10 to the negative 6. Of course, there are more. I just didn't bother writing them down. Right. So then 0.0043 plus minus 1.960 times the square root of 2.0357544484 times 10 to the negative 6. Don't forget the square root. Once you take the square root, you'll get 0.0014267986884. That value is the standard error of the difference in proportions. So this is the standard error of P F hat minus P P hat. Yeah. If you prefer, you could have calculated the standard error on the side and then tossed it in here. It doesn't matter. Yeah. In the end, we end up in the same place. So what I get is 0.0043 plus minus 0.00279652542. I write out all those decimal places so that when you're working with your calculator, you can work through and check that you get the same values. Because, right, if you're not getting the same values, then you did something wrong. Yeah. Okay. This is my margin of error for the difference in the proportions, right? 0.0028, let's say. Remember how we write out a confidence interval? We have to use round brackets, the lower bound, comma, the upper bound. So that means that you should always start with the minus just to make sure that you're not tripping yourself up. Okay. So what we get is and I'm not going to write out all the decimals, we will use a rounded value. So negative 0.0070965 up to negative 0.00150347. But if I round this to 4 decimal places, let's say negative 0.0071 up to negative 0.0015 to 4 decimal places. I don't know what it is. I always get tripped up with the negatives, right? Because you want to make sure that this one is in fact less than this one, right? And so, okay, negative 0.007 is further away from 0 than negative 0.001. Right, so just kind of check yourself, I guess. But they always trip me up. This is a confidence interval for the difference, right, in proportions. Yeah. So here, this is the difference in proportions. Or more specifically, right, the difference in the proportion of people who have heart attacks while taking fish oil versus the proportion of people who have heart attacks while on a placebo. Ugh. Interpretation is a little bit sneaky, right? So, or more specifically, the difference in the proportion of patients who suffer heart attacks while taking fish oil versus the placebo. One thing to keep an eye out for is this interval is all negative, right? So on a number line, and that might be helpful, right? Especially because we're in the negatives. Like I said, I avoid negatives like the plague, and I don't know why, it makes no sense, but. So if I think about 0 here, right? Then I can jot down my interval here, negative 0.0071 to some negative 0.0015, right? I'm 95% confident that the difference in proportions is somewhere in there. Okay. Could you use this to test the hypothesis? Is there a difference in the proportion of heart attacks in people who take fish oils versus the placebo? Yes, you can use a confidence interval to test the hypothesis, right? At least informally, right? Because if there was no difference in the proportions, then the difference would be 0, right? But we just said that we're 95% confident that the difference does not include 0, right? It's consistently negative. So then, right, we would conclude informally that there is a significant difference in the proportion of people who have heart attacks while taking fish oils versus placebos. Oh boy. All right, I think we're ready to interpret this interval. So what I'm going to do is we're going to use that kind of blurb that I gave you. I want to show you that it still applies. It's just the wordiness for the difference in proportion that adds an element. Okay. So let's interpret the interval. We are, and I'll use a different color for the fill in the blank spots, right? 95% in this case, because we made a 95% confidence interval. We're 95% confident that the interval from negative 0.0071 to negative 0.0015. And I want you to use the word captures, right? Because our goal is to try to capture the population difference in proportions. We don't know what it is, right? But we're 95% confident that this interval captures the true, and in this case, the true, and true is kind of a key word for population, right? So the true difference in proportion of patients who suffer heart attacks while taking fish oil versus a placebo. Remember how I said earlier, it doesn't matter the order that you do the subtraction, right? Or the order of the groups, as long as you're consistent. Okay. And so let's go back to our calculation and just confirm that. So here, right? This is group 1 and this is group 2. A plus B is the same as B plus A. So the order doesn't matter here as long as I'm not, mixing and matching, right? So my standard error is going to stay the same. If I reverse these, right, then I'm just going to get a positive value, right? This is going to be positive instead of negative, but that's the only difference. They're still just as far away from each other. Okay? So we could have reversed these, right? Reverse group 1 and group 2, if you think of it that way, and gotten positive values, right? But because it's a difference, right? The negative just tells me which one is larger, right? And because it's negative, it means that the placebo proportion is higher, consistently higher than the fish oil proportion. Yeah. So or we could think of it this way. So this interpretation, I'm totally fine with, right? Because you will have to write an interpretation. And so this one you're good, right? But if we want to expand our minds a little bit, so, or we could think of it this way. Right? If we think about how we got that difference of proportions, p hat f minus p hat p, right? This difference, right, even in the interval, is consistently negative. The difference is consistently negative. So what I could do is I could say, okay, this difference is less than 0, right? And we saw that on the number line, right? So, okay, this is only if you want to do it mathy, right? But you can rearrange this and you can say, okay, the proportion of the fish oils is less than the proportion of people who have heart attacks on the placebo, right? How much less? Well, 0.0071 to 0.0015, right? That's how much less. Right, so this, if I'm gonna reword this, right, this says the proportion of patients who suffer heart attacks while taking fish oil is less than the proportion of patients I should say who suffer heart attacks, so wordy, who suffer heart attacks while taking a placebo. Okay. How much less is less? We're 95% confident that it's between, oops. We are 95% confident between where are those numbers? 0.0071 and 0.0015. I guess they would be reversed now that they're positive. Right. You always want to make sure you do them in the right order. Okay. How can I write it properly? Right, so another interpretation then is that we're 95% confident the proportion of patients who suffer heart attacks I'm going to start by saying while taking a placebo because I want to talk in terms of the positive. taking a placebo is between 0.0015 and 0.0071 higher than the patients taking fish oil. That one takes a little bit more massaging, right? But if you can get there, that's great. But you're welcome to just use that first blurb that we used. Okay. So like I showed with that number line, right, we can use confidence intervals to test hypotheses or do hypothesis testing, at least informally. Okay. So we can use confidence intervals to test hypotheses, or I'll say to conduct informal hypothesis tests. If the question is there a significant difference in proportion, in the proportion of people who have heart attacks in the fish oil group versus the placebo group, right? So is there a significant difference? That significant difference is leading us down the path of a hypothesis test. So is there a significant difference in the proportion of patients who suffer heart attacks in the fish oil versus placebo groups? Our null hypothesis, even though we're not necessarily going to say it, right? If there's no difference, the null hypothesis is always a statement of no change. We have to assume that there's no difference until we have proof otherwise. If there's no difference, what's the value of the difference? It's 0, right? So in terms, I'm going to steal this number line that we drew. All right, so here, this is the difference. So 0 is the difference. Pf hat minus P hat equals 0 if there is no difference. And maybe I'll remove the hats actually. Just because we're hypothesizing not just about the sample, we know about the sample, but we're hypothesizing about the populations, right? The difference in the populations. Okay. So if there's no difference between the two, then they would be 0. Now, how we can look at this is we can say, okay, well, I see that I'm 95% confident that 0 is not in this interval. So then there's a 5% chance that I'm wrong, right? That's the same as the alpha level, right? So they meet again, right? And so, right, either I'm 95% confident I've captured the population difference, right? Or there's a 5% chance that I'm wrong, same idea, right? But if 0 is not in the interval, then I would have enough evidence to reject H naught, and I would say, okay, then there is a significant difference in the proportion of patients who suffer heart attacks in the fish oil versus the placebo groups, just as an answer. How I would say it is, I would say, since the difference of 0 is not, and I'll underline the not, is not contained in the interval, we can conclude there is a significant difference. There is a significant difference in the proportions. Get a little lazy there. Okay. So we can use confidence intervals to check hypothesis testing, which also means that your hypothesis test and your confidence interval should match up. They should give you the same conclusion, right? So if you're doing both, then you can kind of use that to check against each other. The only time it's not going to work is a confidence interval is basically a two-sided test, right? Because it's an interval, so you're going out into both tails. So if you're doing a one-sided test, it doesn't always match up, but you don't need to worry about that. All right, so we'll pick up tomorrow. We'll do hypothesis testing. If you have any questions, let me know. Otherwise, I'll see you mañana.